Okay, so we start the class. Do you have any questions about homework or last lecture? The homework is due tomorrow, so you can still ask questions in tomorrow's office hours. Yeah, I appreciate if you turn on the video. I heard that some of you are driving because of the terrible traffic. So today I want to do the chapter 3 lab, that is basically some R implementation of linear regression. Then after that, maybe we have exercise, or if you want to go to next chapter, maybe we can go. So I will ask you which one you prefer. Okay, so first I want to finish chapter 3. So chapter 3 lab has slides, but I'm using the R session to show the code. I close it. Yeah, so okay, so we use the famous Boston dataset. So at first you have to install the library MASS. So just for Boston dataset. So if you have already installed MASS, then that should be fine. And if you haven't, then you can do package and package installer, then go on. Windows has slightly different interface. And the Boston dataset is actually the capital B is this. So the last column is the median value of the house. Okay, so each line means each town in the Boston suburb. So the sample unit is one town, and this is the median value of the house, and in thousand. And this is from 1970 or maybe late 1960s. So the houses are really cheap. Even in Boston suburb, the median value is the $24,000. So now maybe it's more than 240,000. But these are the median values, and other variables are basically predictors to explain the median value, the house value. So first one is crime rate. The second one is the zoning, or just zone. And this is the some maybe distance to industrial area. You can see the exact description in this. Actually, the ZN is the proportion of residual land zoned for lots over 25,000 square feet. And in INDUS is proportion of non-retail business acre per town, and CHAS is the Charles River dummy variable if equal to 1 if the tract bound river and 0 otherwise. The Americans prefer the waterfront property even if it has higher risk of flooding. And NOx is some environmental factor. So nitrogen oxidase concentration. And RM, average number of rooms per dwelling. And age is proportion of the owner-occupied units built prior to 1940. And so the age of the building. And the DIS is the distance to 5 Boston employment centers, and RAD, accessibility to radial highways, and tax, property tax rate. So some towns have higher property tax. Usually, if we have more commercial or industrial areas, then the town has revenue from non-residential taxpayers. So the tax rate is lower usually. And the PT ratio, pupil teacher ratio by town. This is hard to use variable generally. So of course, the more teachers is better, right? But also the popular school district attracts more students, makes the pupil to teacher ratio higher. So it's hard to deal with this variable. And the black is, this is complicated variable, 1000 times the proportion of the blacks minus 0.63 square. I'm not sure, but basically the distance from the 63%. I don't know why this variable is used. L stat, lower status of the population percentage. It certainly affects the median value. I mean, certainly explains median value, may not affect. But, yeah, so these are variables. So our objective is to make a model to explain the median value of the house. Okay, so to use all variables without specifying the data set, we attach Boston. Then as a starter, we can do one regression model. Generally, the lower crime rate means median, the higher the house price. So we expect that the coefficient is negative, and we fit. And if we type just LM1, remember that we see we get intercept and crime rate, and we have the summary of LM1, then we can get this. And actually, we have the negative 0.41 is the coefficient. So the interpretation is if crime rate is, say, 1% higher, then the median value is 1%, so 0.0041 thousand lower. So it's not much.
I have a question.
Yeah.
So for crime right there,
Mm-hmm.
which value is the correlation coefficient?
Correlation coefficient is, yeah, that's a good question. And the correlation coefficient itself is not given here. So correlation coefficient, okay, so we tried the correlation coefficient. This is negative 3.88, but this is the coefficient. So median price, house price is basically 24.03 minus 0.41 times crime rate. And remember that the negative, the 0.41 is this one multiplied by the standard deviation of median house value divided by standard deviation of crime rate. Maybe I can just calculate it. So standard deviation of median house value divided by standard deviation of crime rate. Okay, so this is the one. So correlation itself is not shown here, but the correlation and this coefficient of crime rate is just the different, only in scale of the median value and the crime rate. Okay. You know, often the computer scientists standardize all variables. So just that we divide median house value by standard deviation of median house value, then variance becomes 1. And also the crime rate, the predictor by standard deviation of crime rate. So every variable have variance of 1. So that is one way to analyze data. So in such a case, correlation coefficient and the coefficient of crime rate is the same value, but here we have different scale for different variables. So we have adjustment here.
So the correlation coefficient is
negative 0.388.
And then the negative 0.4151 is
this one, yeah. So the
okay,
coefficient
Thank
in
you.
linear regression relationship, yeah. Yeah, in Twitter, one famous economist said that the correlation coefficient and the coefficient of the linear regression are the same, but actually it's different. So if these are standardized, then it's the same. You can see the maybe start 20-10 textbook to see it. Yeah. So you can say that the correlation coefficient is negative, then this coefficient of predictor is also negative. At least you can say that. Or correlation coefficient is 0, then this coefficient is also 0. Okay, so the next one. So this time we try the confidence interval for this regression line and the prediction interval of regression line. So we can make okay, so we can make a scatter plot in this way. Okay, so this is a little bit problematic. So more numbers are concentrated at 0. So maybe we need some transformation of this X value, I mean the crime rate, because the many of these are really close to 0. Yeah. Then, okay, so we can get this regression line. Okay, so this makes poor sense. Maybe it makes some sense, but it's not the best thing to do. But okay, so we want to see how reliable this line is. So that is called the confidence interval. So if data changes a bit, then this regression line also will change a bit. Then what's the area where the regression line can go through? That is the confidence interval, in short. So we want to develop this. So confidence interval for LM1. Okay, now we see 0.99, so 99% confidence interval. So that means we have the true line. We don't know the true line, but we have a true line, and with 99% probability, the true regression line is within this confidence band. Confidence interval, maybe confidence interval level. I think that this shouldn't have quotation symbol. So this means that, sorry, the confidence interval. So before that, before confidence interval for the entire region, the confidence interval for each coefficient. So we have estimated this regression model, and the 24.03 is the intercept, and we want to have the band for this intercept. So we can say that the true correlation, true intercept is between these two numbers with 99% probability. And also this -41 is within this range with 95% probability. So we can say that we are not exactly sure if this is really equal to -0.41, but we can say that this coefficient is between -0.5 to 8 and the -0.301. So that means at least it's negative, at least less than -0.3 with 99% confidence. Okay. So next, we want to have the basically the region where the true regression line goes through. That is the confidence band. We name it as the CI. We can use the predict function and LM1 and interval confidence. So this is the 99% confidence band. So maybe we can see this head of this. So that means, okay, so yeah. So first observation have the some X values, so crime rate. So 0.00632. So the first observation 0.00632. So okay, so maybe see the histogram. Oh, actually, the crime rate is not really reported in ratio, but actually reported in percentage. Okay, so 0.00632 is very low. So very low. Then, so in this, with this crime rate, the median house value is between 24 and 24.83. So you can see that we maybe again plot heavy line. So 0.0, almost 0, right? So in such a case, okay, so this estimated the median house value is about maybe 23, but actually it should be between the 24 and the 20, actually maybe 24, but the 24 point something, but actually that should be between, between 23.2 and 24.8. So 23.2 to 24.8 or something. So that means that this line can fluctuate, but not much. Maybe it can go upward by 0.8 or go downward by 0.8, but not much. And this is for each observation. So the second observation, the crime rate is, okay, so maybe you can again see the head of the Boston dataset. Then these are crime rate. So actually the first 6 towns are all a very low crime rate. For these crime rates, then the expected, the median house value is this, almost 23.2. Maybe it's a little bit obvious. So maybe Boston dataset have 506 observations. So maybe we can see some other ones. So 501st observation to 506 observation, crime rate is 0.22. Maybe still it's not really high. Crime rate, actually they're pretty low. Max crime rate, 88. Okay, so crime rate is here, so still not really high. So we can see some crime rates are higher. For example, maybe 200, maybe 428th observation. 428th observation has crime rate of 37%. So then you can see the expected house value is much lower. So the expected value is 8.39, and with the lower bound, the 5.36 to 11.4. So that means that this line changes a bit. Then at x is equal to 37.6 around here. So this line should go through between 5.38 to 11.4. So that is what the confidence interval means. And yeah, so you can make the band based on this confidence, confidence band information, CI. So for each value of x that we have the range. So if we connect this range, then we can make an area. So we can do this. And the one, so basically we want to plot this one and this one. But if we use just these ones, we have some trouble. So matplot crime rate. And the CI, type L. color 1, 2, 3, line type 1, 2, 2. Color 1, 2, 3 is the black, red, green, and the line type 1, 2, 2 is the solid line and the dotted line. Then we plot this, then we have this. So basically the black one is the original one. So the regression line. And this red one and the green one is the lower bound and upper bound of this regression line. So this means that we have so many observations at around crime rate is 0. So around here, estimation is reliable. But if the crime rate is much higher than the center of the data, then just a slight difference in slope becomes larger error. So this part that we have wider ones. And okay, so this doesn't look too bad, but you can see that we have the strange duplicated line around here. So this is actually the dotted line, but we have the many dotted line here, if you see it, because we connect the confidence band at each crime rate in random order. So maybe the first band is here, and the second band is here, and the third band is here. So just this connects this point, this point, this point, this point, this point, this point, and so on. So just connect it in a random order. So that's why we have many duplication here. So better way is to order crime rate and the confidence interval in the increasing order of crime rate. So we can at first define the order of crime rate. Then we put order in this way. Then we can see just one line, and one line. So here the crime rate is a vector, so we specified just order. But the confidence interval consists of the 3 columns, the fitted value and lower bound and upper bound. So this is a matrix. So matrix have 2 indices. Then first one is the row number, and the second one is this 1, 2, 3. So we pick 1, 2, 3 all columns. So just we put the order here, and the second one that we just leave as blank. So that means that we take all columns. And this matplot function is similar to plot function, but we can deal with the multiple columns in this way. I think that to overlay the scatter plot with this is a little more complicated, maybe because the matplot basically reset this window. So if we want to overlay this at first, we can at first we can do this way. Then after that, we have to put the lines. But if we just put this, then just we have new graph, so it does not work. So probably that we can do that the parameter new is equal to true. So overwrite graph. Then the matplot, but probably it does not still work because basically the scales are different. So you can see that the scale should be maybe 0 to 100 or something, but here we have the different scales. You can see 0, 30, 10, 40, 20. So basically we put the different scales at the same axis. So we have to have the same scale. So to use the same scale, okay, so this scale is 0 to 50, and this scale is maybe 0 to 100. So 0 to 50 and 0 to 100. So maybe X limit, the 0 to 100, and Y limit, and 0 to 50. Okay. Then this. Then parameter nu is equal to true, then the matplot, and still we have to specify the x limit and y limit. Then probably that we can do this. Yeah. Still, though, we have the two names of the y-axis and the x-axis are duplicated, so maybe we have to we have to correct the name of the axis, but now that we can see what's happening. Yeah, and the second one is the prediction interval. So confidence interval means the range for the true parameter. So based on true parameter, we can make a true regression line. So the green band and the red band means the true regression line is in between these two boundaries. But the another thing we want to do is the coverage of the observations. So what range covers 99% of observations, for example? So that range should be much wider, right? Because this is just a regression line. Even if the regression line is true, the observation have error. So the observations are much more in a wider range. So we want to set the 90%, 99% range for the observations. That is called prediction band. So prediction band, we use the same function, predict function, but we have to specify interval is equal to prediction. Yeah, so we have defined the confidence interval, but now that we want to define the prediction interval, prediction band. Yeah, so warning message isn't an error. So this is a little bit, misleading, right? So that we are using just the data set to see the prediction band, not we are testing something. So just warning message that meant that. So predictions on current data. Yeah. And okay, so now that we can see what is PI. You can see the range is much wider. So last time that we have the fitted value of 20.03, that's the same. Lower bound is 23.2, upper bound 24.8. So almost the same as this number. But here, we also consider the error of each term. So if we include error, the band should be much wider. Oh yeah, computer, sorry. You can always speak up something. I cannot really see the chat all the time. So
I had a question actually.
Oh yeah, sure. Yeah, go ahead.
So whenever using the predict function, does it automatically use level 99%? I thought it was 95.
Oh, that's a good question. So oh, sorry. Oh, you're right. So the default is 95%. Sorry, so I would say that 95%. And if you want to change the 99%, then we have to specify the conf int is equal to 99%. Then it becomes 99%. I think 0.99. Yes. 99%. Yeah. Sorry. So yeah, I was wrong there. So without specifying anything, 95%, that is the default. And 99%, we have to change it into this. Yeah. You can see that now we have changed it into 99. So I think it becomes, predict 99%. Actually, it has not been changed. Confidence interval. So default is 95%, and to change it, we have to specify, I thought conf int, but maybe level. Maybe we can try. Yeah, level, sorry, the level. Level is equal to 0.99, then confidence level becomes 99%. So this becomes wider than before. So this is 95%, sorry, and this is 99%, sorry. The same thing applies for confidence interval. So we have calculated 95% confidence interval. Sorry about that. Okay. Maybe we go for maybe 95% for now. 99%, a little bit too large to show as an example, because basically we have to have the 500 observations within the range approximately, right? So that maybe range is too wide. So maybe we go 95%. Maybe we can go even 90%. But anyway, so PI. So we can describe this prediction interval on this graph. So if you want to do that, then we can further plot PI on this. So parameter nu is equal to 2t, then we override. Then matrix plot. And again, the PI, not CI here. And color 1, 2, 3, maybe that's fine. And X limit, and yeah. Then we can see this. So this means that within this band, the regression line should be, within this band. And the larger one here and here, this should have approximately 95% coverage of observations. So we have 506 observations in this data set. So approximately maybe 480 observations are within this range. So that means the 26 observations are out of this range. Maybe one here, so 2 observations, then 3, 4, 5, maybe 6, 7, 8, 9, 10. Maybe approximately 10 to maybe 20 to 30 observations. So it sounds right. But that is just based on the normal theory. And this plot is a little irregular. So not exactly 95% are within this range, but approximately that should be true. Yeah. Maybe it looks nicer if this lower bound and this upper bound have the same color. But anyway, you can control by these options. Do you have any questions so far? So the theory for prediction band and the confidence band are also covered in the 50-30, but at least even if you don't care about the details in the formula, it gives useful information. So what's the range, the prediction band and the confidence band when you do final project, for example. Yeah, and to avoid this, the overwritten the labels, we can specify X lab and the Y lab. If within this matplot function, X lab is equal to quotation nothing, then the X label is not overwritten. So it becomes more beautiful. So next, okay, so this regression is a little bit irregular. So some observations are outliers here. So it's actually the very skewed data. So it's a problem. Probably we should transform it in some way, but at least in this regression, these observations have too much influence to the regression line. Probably if we exclude these 3 observations, the regression line is much steeper, smaller negative number. So we want to see. So if we check the the points with largest leverages, probably that we will have these points, and we want to see which points are these. Then we can use the hot values. Hot values is the leverage. So hot values are here. So the first 6 observations are really around here. So small hot values, but which observations have largest hot values? We can check it by which max function of this. Then 331st observation. So this is the largest one. The observation with the largest leverage. So that means that this observation is 381st observation. Or if you want to see the three largest hot values, then we can hot values of LM1 and the order. Then largest one, so the last 3. Then we can see this. So this means the 381st observation has the largest hot value. 419th observation is has the second largest hot value, and the 406th observation is third largest hot value. So hot values, then we check the order, and we check the last 3 ones. So last 3. So last 3. So just the 3 largest. And maybe we can describe which observation is this. So to do that, we can install the library, the map tools. Maybe loading, yes. Maybe I haven't installed this one. So map tools function. Yeah, it takes some time sometimes. So this seems that the map tools itself is installed, but the required package isn't installed. Maybe. Yeah, so now I think it should be fine. So now we have no errors. Then we can plot. I think the point level. We have already the graph. So point level. X crime rate, the max. So we want to plot just the 3 observations. If we plot everything, it's too crowded. So then we just write the number of the so the observation number for those 3 observations, such as the 381 here. So we just put the label, these numbers as label. Then I think that we have to also specify X limit and Y limit. I'm not exactly sure. Maybe we don't really need it. Okay, so label, point label. Then we can put here. Okay, so this is 381st observation, and this is 406 or 408.19. Also, if you wanna put the name of the town, you can specify the label in that way. Maybe you can prepare some variable, and then I mean you can prepare the names, and you can put it like this. Yeah, so this is how to do the analysis. Probably this is not the best way to regress the line because the crime rate is very skewed. So very skewed. So I would say that I would transform this maybe by the logarithm, but many things are close to 0. So I don't know, maybe log of crime rate here. Yeah, I think it looks nicer. And the histogram of median house value. This is okay. Maybe we want to take the logarithm also. Slightly left skewed, so but maybe the both log scale looks better. So probably realistically, if we do practical data analysis, probably we have to take the log scale for both. Then we can see the more regular data, and we have some tendency, so negative slope. So maybe AB line. Yeah, log of median value and the log of crime rate. Sorry, I didn't put LM. Yeah, like this. So this looks the more reasonable analysis. So it's not affected by these 3 observations. So we can see, we could see the outliers, I mean, the points with higher leverages, but now these 3 observations don't have much impact. If we exclude these, still the regression line is probably almost the same. So it's better, more robust regression result. Any questions? Okay, so next we do ANOVA, analysis of variance. So yeah, so we have fit just the median house value on crime rate, but other factors also are important to determine the model. So we define another model, LM2, median value on crime rate and the distance from city center, and NOx, the environmental variable. So we say this as LM2. And LM2, we can get also the summary. And this. You can see if we put 3 variables, the crime rate is still significant, but also the distance from the city center and the NOx level is also significant. So these 2 variables have additional information. So we can see if these 2 variables are additional information by doing ANOVA. In this case, obviously, these 2 variables combined are useful to explain median house value. But sometimes it's vaguer. So if we use ANOVA function, we can see the overall effect of these 2 variables. So that is often important to deal with the categorical variable. Suppose that we have a categorical variable with the 3 possible values. Then we have the 2 additional degrees of freedom. So if we have 3 categories in a categorical variable, we have a baseline, and beyond the baseline, we have 2 other variables, 2 other categories. So each of those needs the indicator variable in the linear model. So often we have the 2 variables, such as the categorical variable, the level 2, and the categorical variable level 3. So in such a case, we want to see the overall effect of these 2 variables. So in such a case, it's useful to use the ANOVA. And the ANOVA result here, so p-value is the 2.9 to the power 2.9 times 10 to the power negative 15. So of course, this and this are both significant. So overall, it's more significant. So p-value is even smaller. So this is just the overall explanation for the linear model. So now I think that you're at least comfortable to do a basic linear regression analysis in R. Do you have any questions so far? So the Boston dataset is really a popular dataset. So if you see some textbooks, then actually this dataset is used to explain concepts. And also, originally I ran the directed study on the same textbook, and at that time, the students used the Boston dataset to compare the model performance of the all models in this textbook. So we apply the neural network, maybe the tree-based method, random forests, support vector machine, linear regression, and so on to the same Boston dataset and compare which is the best, which model explains the data best. So this is really a nice dataset. So now I think the real estate website provides the API to download the datasets. So you can download the datasets as you want. So you can have much more information. Okay. And 6:18. So do you want to have more exercises, or do you want to go to chapter 4? Maybe I have to make a poll.
Are the exercises going to be on
linear regression? Slightly different functions, but yeah. Maybe. Okay, so maybe short time to discuss with the classmates. More exercise. Okay. Okay. 8 students, 1, 2, 3, 4, 5, 6, 7. Okay. It's hard to decide. Okay, maybe, okay, so we go to chapter 4. We go to chapter 4, and the chapter's additional exercises, it's already on the website. So I will upload the solutions. So you can see there's some other things. Maybe I can just review the what's discussed in that exercise. So exercises does not include absolutely necessary contents, but at least it's useful to see it. So this is exercise 3. So we use the ISLR package, and this the automobile data. So 392 observations with 392 car models. And it has the MPG, number of cylinders, displacement, horsepower, and so on. And we explain, okay, so at first, this is a scatter plot. So we can see the pairwise scatter plot, and we can see tendency. For example, MPG and weight are not linear relationship. We have some curvature. or some variables have linear relationship between, for example, the displacement and weight. We have maybe clear linear trend and so on. And this is useful, but also this kind of correlation plot is useful. So you can see the correlation is higher between the number of cylinders and the displacement. That is clear. And the horsepower, of course, and the weight. Heavier weight, then usually we need a larger engine. So the MPG also have higher correlation, but the lower correlation between, I mean negative correlation between MPG and MPG and MPG, of course, this diagonal term always one. And MPG and the displacement, that we have negative relationship. MPG and weight, the negative. That's natural. Acceleration and MPG, actually positive. It's contradictive, maybe, but maybe the higher MPG, the lighter car, then acceleration is better or something like that. And the year and MPG, the positive relationship, that's natural, and so on. So this correlation plot may be useful when you do analysis with a large data set. You can see all the results at once. Maybe this is more informative, but maybe too much information. And also categorical variables, we cannot really see the tendency like this. Yeah, and this also discusses the stepwise regression we have done in 5030 also. So we start with a large model, for example, and drop unnecessary variables. So that can be done by, step function. Okay, so step function. And basically, we prepare the largest model and we prepare the smallest model, and we do model selection stepwise. So basically, we start with the largest model in this case, LM full model, the model with these variables. Then we drop one variable at a time. And sometimes we add one variable at a time and drop, add, drop, or something. Then to reach the best model. Actually, this may not be the global optimal model, but at least we can get a reasonably good model. Yeah, so in 5030, we only covered maybe step. Yeah, I think this may be covered. Yeah, so we can see the result here. So here, starting with the full model, if we drop the horsepower, then the model's AIC is smallest. That means the test performance is expected to be best. Then we drop another variable, drop another variable, drop another variable, and so on. And yeah, drop acceleration. And here, if we drop any variable, AIC gets worse, much worse. But if we add another variable, then the AIC gets better and gets worse, actually. The AIC gets larger. So we do nothing is the best. So then we stop the procedure, and this is the final model. So final model is named as LMS. So formula. So we fit what? The MPG. MPG is explained by the weight and the year. Yeah, weight and the year. So only these two are necessary to predict the MPG. Maybe these days a little different, maybe, but just a newer and lighter car has better MPG. That was true in this data set. Yeah, but when we fit the residual plot, obviously we have some curvature, U-shaped curvature. So that means the weight square is useful variable to explain this. Year and residual, maybe we don't have much tendency, and so on. Yeah, so that's exercise 3. Okay, so now go to chapter 4, maybe. We have still 20 minutes. Do you have any questions? So for coding, basically you need more examples. Right? So probably the practice also sometimes matters, but as long as you have enough examples that you can see their answers. Yeah, and also in the last part of this exercise, I calculate everything from scratch, such as degrees of freedom or residual standard error or multiple R squared. But when students in my class did excellent to calculate everything from scratch. If I teach a class in business school or Department of Economics or biology, maybe this kind of questions are difficult, but most of your math major or computer science major or at least some quantitative measure. So as long as you have definition, basically most students are very good to calculate these. If you're interested in, you can see it, and you can see from the definition, you can get the same answers as the LM function. Okay, so go to chapter 4. So chapter 4 is classification. So we discussed a little bit about logistic regression in 5030, but basically that we discussed the classification in more detail, and also logistic regression, I fully explain it from scratch, because the other classes, even they discussed logistic regression, and it's just minimum. So that I discuss a little more about logistic regression. And of course, the logistic regression is for only two groups, like yes and no, or malignant and benign, or default or not in default. So if we have more than 3 categories, this may not be a good idea to use. And we have other methods, such as linear discriminant analysis and the quadratic discriminant analysis and the k-nearest neighborhoods. Yeah. So these methods can be used for more than 2 categories. And also logistic regression has extended version, which can be used for more than 2 categories. So examples of classification. So the famous example is categorize the handwritten digits or characters into classes, such as 0 to 9 or A to Z. So we have 10 categories or 26 categories. Maybe for Chinese letters, maybe 4,000 categories. And categorize the 150 flowers into 3 species based on measurements such as flowers diameter. So anything, for example, you wanna try to categorize people by, maybe you wanna predict the blood type of the people by some characteristics, then you can do classification. That's probably hard, but categorize the 150 flowers into 3 species. That is reasonable job. Different flowers have different dimensions of the flower, the diameter and so on. And another example, the judge whether or not patients are malignant based on several medical measurements. Yeah, this is binary classification. Or maybe another example, we categorize, maybe we want to explain the rating of movies by other factors, such as the length of the movie, the music used, or other factors. So sometimes these are just categories. So 0 to 9 are categories. 0 to 9 are ordered, but in terms of the character recognition, these are just 10 different categories. And sometimes the category is ordered if the rating is the response variable. Maybe 1 to 5 means 2 is better than 1, 3 is better than 2, 4 is better than 3. Yeah. Okay, so the first example, the default status of customers of financial institutions by balance and income. So balance of the debt is here, and the income of the consumers are here. And the circles are not in default, and these pluses are, these crosses are the in default. So you can see the balance is larger, then more people are in default. Income does not really matter. It looks. If we think about the profile, then we can see it clearly. So this is the default status by balance. Obviously, the not in default, the balance is much lower than this group. So this is box plot. So this box includes the 50% of observations, 50%. So this is called whisker. So it's not very meaningful. Basically 1.5 times the box size. But the whisker is shorter if the observations are not between 1.5 times the size of this bin to this point. Then whisker gets lower, shorter. So for example, this one, this whisker is much shorter than 1.5 times this, but that means the 1.5 times is around here, but the no observation from here to here. And the income is not different between these two groups. So for binary classification or multi-category classification, sometimes it's good to see this profile. Yeah, binary classification problems can be fit as regression models, such as logistic regression. We will discuss it in the next section. And it is hard to apply a regression model to classification problem if there are 3 categories, such as blood type. Maybe pairwise that we can fit A versus B, B versus O. For example, we have 26 letter recognition problem. Then we compare A and B, at least. Okay, so suppose that the letter is either A or B, then what model we can use? Then we can sequentially, decide which character is A and which character is C, and so on. Yeah, so even if the category is ordered, still it is not easy to see how to quantify the result. So even if we have the rating of the scale of 1 to 5, we don't know how much better 5 is compared to 4. Maybe difference between 3 and 4 is small, but the 4 and 5 is large. That's possible. Yeah, so generally, if these ratings, for example, 1 to 5 are just numeric numbers, then that's easy to deal with. I mean, for example, I don't know. Suppose that we measure the temperature of the places, and all temperatures are from maybe 1 to 5. Then just the difference between 1 to 5 and 1 to 2 and 2 to 3 is exactly the same, physically the same. So in such a case, it's easy to quantify the variable, but the rating 1, 2, 3, 4, 5, maybe it's ordered, but the interval is not clear. So in such a case, we have to be careful, and we have to use categorization technique. Okay. Any questions so far? Okay, so now we go on to the logistic regression first. This is only for binary classification. So suppose that Y is binary and X is predictor variable, which is either quantitative or qualitative. Yeah, then also that we define that the probability of Y is equal to 1 given X is P of X. For example, X is balance of debt, then y is equal to 1 is in default. 0 is not in default. Balance is larger, probability of default is larger. So P of X, P of 1,000 is maybe only 1%, but the P of 2,000 maybe 3%, P of 3,000 maybe 6%, and so on. And logistic regression formulates the probability of X by this function. This is called logistic function. F of A is e to the power A over 1 plus e to the power A. So what happens if A goes to infinity? As A goes to infinity, what value FA approaches to? Any?
Would it be 0?
A goes to infinity, I mean.
Oh, okay. Yes.
A goes to negative infinity, this goes to 0, this goes to 1, 0 over 1 is 0. So F negative infinity is 0. If A goes to positive infinity, what value this approaches to? Anyone? Yeah, I think someone almost said that.
Infinity?
Not infinity. Maybe you can plug in just number like 100. E to the power 100 is 2.718. Okay. E to the 100 over 1 plus e to the 100. Anyone else? Maybe
1.
1, yeah. So 1, right? So this goes to infinity and this goes to infinity and the same value. This 1 plus is almost ignored. So F of A goes to 1, right? So the graph is like this. So goes to negative infinity, it's 0. Actually, just negative 4, negative 5, almost 0. And positive 4, positive 5, almost 1. So the response is always 0 to 1. So it's not reasonable if fitted value goes negative or fitted value goes to more than 1. We are predicting, we are, explaining probability. Probability is between 0 and 1. So we need a curve which goes to 0 as x goes to negative infinity and which goes to 1 when we goes to positive infinity, if x goes to positive infinity. Maybe the other way around is possible. The goes to 1 as x goes to negative infinity and goes to 0 as x goes to infinity. That's possible, but we need this kind of curve. Yeah. So that's the point. So we can see that the situation is like this, the balance and the probability of default. And our observations are either not in default or in default. So response values are either 0 or 1. So if we fit the straight line, that does not make sense. So what's the meaning of fitted value of negative 0.1? The value is either 0 or 1. So negative 0.1 cannot be optimal estimation. The probability should be between 0 and 1. So we wanna have this kind of line. So each value of balance that we have the fitted probability. So around here, almost 1% or 0%. Around here, almost 50%. Around here, maybe almost 100%. Do you come up with any other functions which can be used for this purpose? So this shape is necessary. Maybe slightly different shape is fine, like this or this. So if you have taken probability theory class already, 5700, then you can see this is the cumulative distribution function of some random variable. So any cumulative distribution function, continuous cumulative distribution function is used. For example, the normal CDF or Laplace CDF or FCDF or T distribution, CDF of T distribution, anything can be used. But logistic regression has some good properties when we optimize the model. So finally, we have the objective function, and that becomes convex if this is a logistic function. So basically, the famous example is this logistic curve and also normal CDF. Those are probably those are famous. And also the arctangent. So tangent is like this graph, right? Tangent is like this. And if we think about the arctangent, it looks like this. Maybe range is slightly different, maybe negative pi over 2 to positive pi over 2, but we just adjust that range into 0 to 1. The arctangent can be used. And computer scientists often use arctangent for this purpose. Yeah, so one mathematician joked that after you graduate a school, then you don't use the cosine curve and the sine curve, but we need arctangent curve because we need it in this logistic regression and the neural network and so on. Yeah, so that's the point. So our idea is that the P of X is this F of beta naught plus beta 1x. So if predictor value is larger, then if beta 1 is positive, then probability is higher. So we can model the relationship between, probability of y is equal to 1 and x value in this way. If we don't have this function f, then probability goes beyond 1 or less than 0. So that is not reasonable model, but this is reasonable model to predict a probability. Yeah, so this is the default data set that we have discussed in the previous slides. So we have several variables, the default status and the student status and the balance and the income. So default is response and the others are possible predictors. So each line means each customer. So logistic regression, we have done that. Yep. Yeah. So now we want to interpret the coefficient. So we have the complicated function f. So we cannot say when x is 1 larger, p of x is beta 1 larger. We cannot say that because it's not a linear regression. So how to interpret it? At least if beta 1 is positive and x is larger than by 1, then p of x gets larger, we can say. But we want to say a little more than that. Then, okay, so we transform this. You can say we can multiply this denominator on both sides. Then we can do something. So we move this times p of x to the right-hand side and divide by 1 minus px. Then we can get this. So this is the odds. So p of x is probability of y is equal to 1. So this is a kind of success probability. What's the numerator? What's the denominator? This is the failure probability. So if success probability is 30%, the failure probability is 70%. So the ratio is this. This is called the odds ratio. So 30% over 70%. The ratio is maybe 1 over 2.3, maybe about 40%, 40, maybe 2% or something. So that's the odds ratio. And odds ratio, okay, if we take the logarithm of odds ratio, the log of this ratio, that is beta naught plus beta 1x. So that means if x is larger by 1, then odds ratio, log odds ratio gets larger by beta 1. So that is the interpretation of beta 1. So it's more complicated. So it's hard to interpret actually. So the relationship is nonlinear. But at least we can say that the beta 1 is positive, then X has positive relationship with probability of Y is equal to 1. Oh, by the way, this function, the log of basically log of the Y over 1 minus Y, that is called inverse logistic function. This is inverse function of logistic curve. Yeah. So so this is, I think, the new material for everyone. So we can interpret the beta 1 in this way. The log odds ratio increases by beta 1 when X increases by 1. Okay, so next time we have more examples on logistic regression and other classification models. Okay, so thank you for listening, and see you next Tuesday. Again, the homework is due on Friday. So if you have questions, you can ask questions after this or office hours tomorrow. Okay, thank you. Have a nice weekend.
Have a good
Hey,
night.
Professor, I have a question.
Sure.
It's about the ANOVA function in R.
Okay.
I can't tell, this might be a dumb question, but I can't tell which one is the p-value in the
Oh,
report.
I see. Yeah, sure. Maybe I will have some maybe exercises. Sorry, not this one. Just a moment. Sorry. Sorry, the ANOVA is in the lab session. Yeah. So,
If you want, I can share my screen.
sorry, yeah, I have one. Yeah, sure.
Okay.
So yeah, this is ANOVA table. Okay, and the p-value is here. 2 point this one. So probability of F is largest. This is p-value.
Okay.
So it reads 2.964 times 10 to the power negative 15.
Okay.
Yeah, and this p-value is basically the upper tail probability of F distribution. Then the threshold of that F distribution is this 35.78. Yeah.
Okay. Okay, cool. Thank you.
Sure.
Officer, I have a question too.
Yeah.
Yeah, it's about the homework. So question 3C. I was
3C,
trying
yeah.
to,
Mhm.
yeah, last time you said there was an error on it, right?
That's right. So I have already corrected in the, yeah, I can share
Okay.
the screen. Yeah, homework 1, right? Homework 1, yeah, homework 1, yeah. Yeah, so it's already correct.
Okay.
Corrected.
So
So
I'm sorry. So the
I
only
think
plot that we have to scatter is the one for TV and sales, right?
yes, yeah. So
Okay.
originally
so
I put in A here, but I just deleted in A.
Oh,
So
okay.
A, we
Now
have
I
more
see. Okay.
complicated
Yeah, because I
scatter
was
plot.
kind of
Yeah.
confused. I was like, I know he said that there was an error on it, but
Yeah,
yeah,
it's
I
already
couldn't figure it out.
corrected. Yeah.
All right, thank you. So on 3D, I was trying to use AB line, right?
Yeah, yeah, AB line, you can use
So,
it.
yeah, because on 3C, that's what I did. On 3D, I was trying to use I'm sorry, yeah, plot, resid, and then TV for the horizontal line, and then residual of LM2, because LM2 is my regression of sales on TV.
Sorry.
Okay.
Sorry, which question are you asking about?
3D.
3D.
Yes.
Make a residual
So,
plot. Yes. So the TV, yeah. So you can use the result of 3B to do this. Make a residual plot. Yep.
okay.
Yeah.
Yeah.
So the
It
yeah.
wouldn't- I will try again, but I don't know why it wouldn't plot the residuals. But yeah, I'll just try again. Because my regression is, yeah, sales on TV, right?
Sales on TV. Yes. Yeah.
Right. So I was trying to plot the residuals on it, but it wouldn't let me. I will try again. And then if I have any error on it one more time, I'm going to come tomorrow to the office.
Okay,
I'll
sure. Yeah.
fix it. And the x-axis, can I just do AB line, H equals 0 or 0, 0 for the x-axis?
Sorry.
So they want us to add the x-axis on the plot.
Oh, yeah, x-axis. Yeah, x-axis is 0, 0, right? So y is equal to
Okay,
0. So
yeah.
y
So
is
that's what
equal
I
to
was
0
thinking
plus
about.
0x. Yes, yeah, you're
Okay,
right.
so
Yeah.
I'm good. Thank you, Professor.
Sure.
Have a good one.
You too.
All right.